Sir, it's allowed.
Okay, just okay. No, it's not. So let me check in again and I'll do that, sir.
Okay, sir. Share your presentation.
योगराज
Sir,
इनको कायजात साहब को ज्वाइन कराने वो करने दो, प्रेजेंटेशन लगाने दो, ठीक है।
जी।
मैं सेशन शुरू कर रहा हूँ। कायजात, आर यू एबल टू हियर मी?
Yes, sir, I'm able to hear you.
You manage your things. Meanwhile, let me give the preamble. We can't let the people wait. Okay?
Yes, now is my screen visible?
Yes,
Oh
yes.
yeah, it has
Perfect,
come.
perfect.
It
Thank you,
has
sir.
come. Go ahead. Go ahead.
Thank you so much, sir. Thank you.
Okay.
Uh, so yeah, very good morning to all of you, and thank you so much for giving me this opportunity to present. Without wasting time, because we have already, I think, we are wasted some time. So let's just start. So today I'm going to present some case studies, and if you have any questions, I mean, we can discuss as we progress. So the first case study which I'm going to share is about the. Just a second, it's not going further. Okay, it's about the a chimney in a coke oven plant. So basically, what happened? Hello, there's some noise from background, please. Hello. So this is the basically, if you see, this is the coke oven plant, and I'll switch on my pointer so that okay. So this is the coke oven plant, and there was a failure in the boiler. So coke oven plant basically is the steel plant, and there was a failure in the boiler, as a result of which almost a flue gas of 930 to 950 degrees temperature was transferred to this chimney. Now this chimney was not designed to take this kind of load for sustained period. Like this shutdown went on for almost 2 months, and as a result, what happened was the lining inside the chimney just above the duct started collapsing, and that is when the chimney started buckling. Now they do not have an option to shut down the plant. Reason being, if the temperature is lowered below 750 degrees, the bricks in the coke oven are silicate bricks. So they will crack and the plant will stop. If the flue is still going to the boiler, there will be a blast in the boiler because there will be a pressure created, which will be a back pressure. And if they still operate the chimney would collapse. So this is the kind of when we got the I mean we got to know this about this case. This was the condition by then. You can see the chimney, and this is a 90-meter tall chimney, RCC chimney. So this was the condition. The chimney had buckled, the concrete had disintegrated, the steel inside the RCC shell had melted. So this is the condition when they came to us. So what we did was, initially we started doing endoscopy so that we know the extent of damage inside the structure, because we were not able to we could see the buckling of the chimney from outside, but we were unable to see how much extra what extent till what extent the lining has collapsed, till what extent the concrete has been damaged, or what is the condition of the reinforcement inside. So when we opened up, we realized that almost 2 meter in height and 3 meter periphery on each side of the duct was damaged. And you can see the 3-layer lining also has collapsed here. And this was the condition when we closely monitored this. And this was online, monitored online. I mean, we could not stop the plant. So we did endoscopy survey. And this is the condition of the steel you can see inside the structure. Then what we did was, we wanted to make sure that whether the lining has stabilized or is it still collapsing. So we started taking temperatures from outside because every day you can't do endoscopy. It's an expensive procedure. So we started taking temperatures around the chimney about 7.5 meter each on above and below the damaged portion. And we realized that by and large these temperatures were stabilized. I mean, where it was higher zone, it was coming higher, but in some portion where the chimney was intact, it was lower. So that was a good news for us that after some initial collapse, it is stabilized. So only that portion is damaged, and we need to take care of that portion. So what we did was we developed a system because in a chimney you cannot do any kind of you cannot open the foundation because it will collapse in overturning, and nor you can do any kind of jacketing from outside because again because of heat it will not last. So we designed a complete steel skeleton from outside. So what we did was we bypassed the top. See, this is the portion where the problem was. So we bypassed that top portion and built a frame which will connect the top and the bottom and bypass that middle damaged portion. So of course, this system was accepted by them. They are principal consultant. But the question was, how do you fill up that with some supporting calculations or something? So I'm not going into much detail of the calculations. I mean, we can discuss definitely when we have time. So what we did was we gave them the complete calculations, and on field we had a couple of challenges. That the first challenge was that there would be reinforcement in the chimney. So when we are fixing this frame system, we'll have to do almost 4,500 anchors. So while we are anchoring, we may puncture reinforcement. So what we did to avoid that was we did GPR. GPR stands for ground penetrating radar. And how it works is that it's on the principle of every metal has got a different dielectric constant. So when you scan that, when you go through the reinforcement will show parabolic shapes. So by that we can identify the location and the probable size of the reinforcement and the cover depth as well. So based on that, we selected locations for anchors, and we drilled 4,500 almost 4,500 anchors, none of which punctured the steel. So whatever steel was residual, we maintained that. The second challenge was the profile, because chimney from bottom to top is in slant, and second thing, it had buckled. So it was not in a straight line. So we did 3D scan of the chimney, and by that we got the complete profile of the chimney. So sections were bent according to the shape. I'll just show you a short video of, so this is on the left, what you see is the work in progress. And, this is the video of work in progress. So you can see here also you can see the base plate is somewhere else, here it's somewhere else. Even the holes in the base plate are. So what we did was initially we drilled holes, then we took a template, and then the entire, the steel structure was made according to that. So basically this is a stopgap arrangement. So what they wanted was that till we build a new chimney, this should suffice the need. And future, when we have a new chimney, probably we'll shift the flue ducts to that and use that chimney. So they wanted this arrangement for almost 1.5 years. So we did that. Now the question was whether in this 1.5 years, if the lining would collapse, how would we know? So to overcome that, what we did was we fixed sensors in the chimney. Like we had strain gauges, we have deflectometers, tilt meters, we had temperature meters, we had wind meters. So everything was connected to a system through a data logger, And from the data logger, we had wireless connection so that on all the mobiles and their control center, they had a command and control center there in the plant. So this data would go there. And we set a threshold limit. Supposing if my permissible deflection is maybe 80 mm, I would set it at maybe 25%. So maybe I would set it at 20 or 21 mm. So if the deflection goes beyond that, or if my values goes beyond certain permissible limits, I would come to know that. And I would also know the reason why it has happened and what is happening. Supposing if temperature rises, then also my strain value will change. So I would know whether it's because of the wind, because of the temperature, because of any other, of failing of lining. So that would be known by this system. So we developed this system of monitoring that online. And for almost 1.5 years, we monitored. And after that, they discovered that, this chimney is running very well. And as it is a standby chimney, can we not repair it? Because cost of building a new chimney was coming almost 15 to 20 crores, plus the inconvenience of shifting the ducts. And again, the process, the efficiency in the process also was dropping down. So then they decided, why can't we use this chimney? So right now we have reanalyzed this structure. I mean, presently we are doing that. Maybe in the next session in the future, if we do, we'll come out with that also. I mean, we'll have that work completed. So what we did there was, we are building a small standby chimney, steel chimney there, diverting the flue through that, temporarily to that, and we'll remove the entire lining from inside, do jacketing from inside, and do lining inside, and in the cavity of the lining, we'll do additional jacketing. So we'll strengthen the chimney also. We'll do a lining which can take temperature up to 1000 degrees, and that's how we can, reuse this structure without even increasing any kind of dead load, because the present lining is about 500 mm. So we'll reduce it to 400 mm, which can take 1000 degrees, and in 100 mm we'll do jacketing. So that would probably be say 80 to 90 days project for us. So for that much time, they'll have to have a small standby chimney in steel, which probably they can use it in future also as a standby chimney. So this is the structure. Almost after 22 years now. So this is the condition of the structure. So any questions you have in this structure, or should we go ahead and then take questions last? Yes, sir.
Sir, did we replace the brick lining inside the chimney?
Sorry?
The brick lining inside the chimney, it was
Yeah.
totally damaged, right?
No, only in some portion.
I see. So that some portion did we replaced or not?
No, you can't go inside because the temperature
Yeah.
inside, even if they block the chimney,
Hmm.
because the boiler is on, the chimney is not working, right?
Yes, yes,
It will
yes.
go through the boiler, but then
Yeah,
the temperature will be around 300 degrees. You cannot go
correct.
inside the
We
chimney.
can't go inside. Yes.
No, you can't.
So my question is that the damaged portion of that brick lining, again that temperature will not impact the concrete structure again
No,
further?
because in that portion, your concrete is already gone. So we've left it that way only.
I see. Okay,
It is
fine.
not, yeah, it's not there. So
Okay.
we kept the holes as it is so that it's allowed to vent out.
Okay, understood.
Yeah. Any more questions, or should we go ahead? Okay. We go ahead to the next case study. Even if you have questions later on, please, you're most welcome to ask. So this is an offshore structure we are doing. And this structure is in Dahej. And Dahej, mind you, is the one of the most riskiest port in the world, because the tidal variation here is almost 10 meters per day, and it has very high wave velocity, and again turbidity is very high. So you cannot see even 1 feet away from, when you are in water, you can't see 1 feet away also. It's so turbid. Water is so turbid. So this jetty is used for a movement of material, raw material and finished products in plant. So this is the heart of the plant. I mean, if this stops, the entire operations will stop. And the approach is almost 2 kilometers, and then the main jetty starts. So the problem here was that so the main thing in jetty, you have to be very sure that whatever you do is, because you're dealing with high tides and sea. So if you look, I mean, if there is any accident, it will be fatal. So you have to be very careful in designing right from your scaffolding, because scaffolding is hung. It's not from the bottom to top, it's top to bottom hung. And you design in such a way that it can take care of the tidal wave. So now you can see this is dry. This is near the approach. So this is dry. And suddenly you'll see water up to the beam bottom. So the tidal variation should be considered, wave velocity should be considered. And again, the live load of people working that also has to be considered. So initially what we did was we did testing. So what the problem here was that they used to repair it regularly and the damage would always reoccur. So every couple of years they would redo that, repairs. They will keep on doing those repairs again and again. So the problem was they didn't get to the root cause. I'll explain you what I mean by that in further during the presentation. So what we did was we conducted some tests on that. That is hammer test, UPV, tomography. So tomography is a much more advanced of the ultra pulse velocity test. It's like you compare X-ray with CT scan. It'll give you exact location of voids also. This is the tomography test that we are conducting. It'll give you the exact location of voids inside the concrete, and almost to a depth of 1.5 meter you can know there. Then this is the GPR machine, which will tell you the position of reinforcement cover. Because in offshore structure, what is more important is also the cover. As per the codal provision, you should have at least 75 mm of cover in this. Whereas in some structure, when we audit, we only see sometimes 5 mm, 10 mm. So this is also one of the reasons why the concrete structures prematurely fail in corrosion. Then this is the core test. So we know the exact strength of concrete. And this is for corrosion. We are doing the I-core, which will give you the potential, which will give you the corrosion rate, and all those in graphical representation. So after we did our audit, we came to a position that we knew exactly what went wrong. And see, these were the photographs of the repaired portion, you can see. And in a jetty, because of the chloride environment, you will have chloride-induced corrosion. And below water, you will have erosion, because if your tidal variation is so high and your wave velocity is high, because of the sand, brushing the surface of the concrete and the steel liners, there'll be erosion. So the top photographs, all you see is corrosion, and the bottommost photograph of the pile on the right hand side bottom corner is because of erosion. You can see how it has damaged the concrete. So this is purely a case of erosion. So what happened here was they kept on repairing the concrete structure without treating the root cause. Now root cause is corrosion, chloride induced corrosion. Let's go a little dive deep into the process of corrosion. So whenever we are casting our concrete, our pH value of concrete is around 13.2 to 13.4. It's highly alkaline. Over the period, as the pH drops, corrosion will be, carbonation will be there, and there will be corrosion on this. And especially in this case, it's a chloride induced corrosion. What happens? And corrosion is basically an electrochemical reaction. So we measure corrosion by passing current. Higher the flow of current, more the potential or the probability of corrosion, I would say. So in this case, what was happening was the corrosion was already there, and they were treating the bar partially. So when you treat your reinforcement partially, earlier it was a 50-50 reaction. Now you treat almost 80% of the exposed reinforcement, and the unexposed reinforcement, which is inside, is not treated. So now it is like 4:1 ratio. So your reaction will multiply, it will not reduce. And that would actually spoil the repaired portion as well. And the one photograph, this photograph, if you see my pointer, if you see, this is the repaired portion. And just near this repair portion, there is again damage. This is a very classic example of halo effect of corrosion on concrete. HALO, halo effect of corrosion. How that works is that whenever you repair a portion with fresh concrete, your pH value of concrete nearby and the potential there is different than your repaired concrete. So it will try to neutralize. And on the interface, there will be a lot of corrosion activity at the interface, which is known as halo effect of corrosion on concrete. So you could see that very prominently here. And again, the piles which were repaired also failed. And here also you can see the corrosion, the cover here is less than maybe 20 mm, which is which is inappropriate for this kind of structure. I mean, you should at least have 75 mm of cover here. Similarly for the beams here. But in the pile, as I mentioned, the case was different. The above water, it was corrosion. In splash zone, it was corrosion. Below water, there is a lot of erosion that is happening, which is very dangerous because that cannot be seen. Below water, you don't see that. Above water, you can see corrosion. So for that, we have divers who go inside and check. So see, this is how the system did not work. See, they added one layer of concrete here. However, the beam in the beam, so they did jacketing, but the jacketing separated from the original concrete. When we dug deep into that, we realized that the grade of concrete which they had used was very high grade. They use almost M60, M80 grade of micro concrete. Now that is not compatible with the original concrete. So normally when when you repair a structure, you should make sure that when you repair in patches or when you repair, when you make up the section, you should make sure that you don't change the properties like, the coefficient of thermal expansion should be there. Then modulus of elasticity should be same. Creep is deformation under sustained load. And fourth is, drying shrinkage. So all these properties, if they're not matched, they would lead to shear bond failure, which is a very classic example here. And then this portion also, new reinforcement was added, but that corroded very fast because of the, difference in the polarity and because the reason they didn't treat the corrosion. And secondly, they were not able to extract chloride, which was already present in the concrete. So that also got diffused from inside to the new concrete. And because of diffusion, you could see a lot of corrosion in the concrete. And here you see also the repaired slab also has, given way. Similarly for the pile caps also. So now what was our approach? How we overcame that problem, right? So we applied a three-pronged or a four-pronged approach. So you create multiple level of defense. How you do that? We expose the concrete wherever it was loose. We removed that. And this, sir, mind you, this was already a repaired portion. So we removed that completely. Then we infuse some corrosion inhibitors in the concrete. How it works is they are bipolar in nature and affinity towards, it has high affinity towards ferrous ions. So whenever you apply a corrosion inhibitor, it will move inside the concrete. And whenever your steel tends to corrode, it will supply opposite ions. Like supposing if there is a cathodic reaction in the steel, it will supply anodic ions. And if there is an anodic reaction in the steel, it will supply cathodic ions. And it will reduce the reaction corrosion. I don't say it will stop totally. It reduces the reaction. Maybe if this is happening in 1 year, that would happen in 5 years. Now, the second line of defense which we use is we apply a water curable epoxy layer, which will cure underwater also, and sprinkle sand on that. Caught sand. How it works is it will chemically isolate the old and the new concrete and physically bond. I repeat, it will chemically isolate the old and new concrete and physically bond. So when you apply that on the concrete, the chloride diffusion from the old concrete and the new concrete totally stops. And because you have applied caught sand, your surface area in contact will increase by almost 2.7 times, and it creates a rough physical bond. So you are creating a bond, whereas you are creating a barrier as well. So that's the purpose. Further, what we did was we fixed sacrificial anodes on this. Sacrificial anodes can be of many type. It can be a hybrid anode. It can be a normal anode. What it does is, if you've seen the chemistry, we have seen that table. So zinc stands, it corrodes before the steel corrodes. So whenever there is current flowing, it will flow through zinc and not through steel, and zinc will sacrifice it, before that. So it is known as sacrificial anodes. And finally, above above water, what we did was we built up this section with micro concrete, which was again, all this material were moisture insensitive materials. Because if you see the data sheet of regular material, they'll mention that moisture level should be less than 4%, wherein jetty it is never so. It is 100% concentrated, and the moisture levels are more than 90%. So after that, what we did was the final step was pile encapsulation. So what we do in pile encapsulation is the diver goes down, cuts the steel section, repairs that balance portion, and then we encapsulate glass fiber piles, which are jackets. So they are basically very high tensile material. So compared to steel, wherein steel Fe4 415 would have a tensile strength of 450 Newton per mm square, this jacket would go anywhere around maybe 3000 or 3500 Newton per mm square. It's a highly tensile material. So you fix up this jacket, and below, from you start grouting from below. So below, by pressure, you pump in underwater curable epoxy paste, which is grouted at a very high pressure. So we grout almost at a 5000 bars. So what it does is it'll displace the water, it'll displace the cavity and fully jacket that entire portion. It'll make the concrete absolutely inert. It'll protect the concrete, and secondly, when you push the epoxy paste at such high pressure, you are actually creating some pre-stressing effect also on the jacket. So my jacket from day one becomes active. Otherwise, my repair will be active only after I increase the load or only if the member deforms. I don't need to do that here. And we have guaranteed this system for operational life of. So similarly, for beams, earlier, if you see, they had done this kind of jacketing, wherein it's a clear failure between the old and the new concrete. You can see this. So we removed that chip that did the entire process, and the beams were deficient in shear and flexure in maybe 20 or 30% respectively. So we recovered that by fiber wrapping. We use glass fiber and carbon fiber here, depending upon the requirement. And now this system is guaranteed for a period of 15 years, no questions asked. So if anything goes wrong with their piles, we will repair it free of cost for 15 years. So yeah, this is, I'm just showing you a glimpse of what we are doing, so you get an idea of different kind of structures and what we did there and why we did that, what we did. So any questions regarding this, or we should move to the next one?
Yes, sir.
Yeah, please go ahead.
What's the name of the chemicals bonding the old and new concrete between?
So see, we had customized this product. So Thermax helped us do that. So I would not give you directly a name of the product because it will be too generic for anything. But you can customize your product as per the requirement, site requirement. You need to customize. And
But
Thermax Chemicals helped us do this. And the piles, we took it from Reliance Composite.
Thermax, which company, sir? Thermax chemical.
Thermax, the company, boiler company. So they have a chemical division.
Okay.
If you want, I'll share the number with sir. You can get in touch with them.
Yes, sir. Definitely, sir. Name of the instrument which is used for the steel spacing checking of the corrosions. Test
So
name of the test.
corrosion, we used ICOR. It's a patented product. Some Canadian company has done that. It's a very good instrument.
Because same problem I had facing in the same problem in Mauritius project. Se, I constructed a jetty in Mauritius.
Okay.
So same problems we are facing. Se, the IIT, IIT, NITK is the
Okay.
principal consultant.
Okay. Sir, you
Uh,
can get in touch with me. I think I'll take your number from Chairman sir and get in touch with you, sir.
yes, sir. Definitely, sir.
Yeah, sure.
Um,
Yeah.
oh,
I had a question.
Yes, please.
This is regarding this the concrete that you are using. Okay.
Yeah. Yeah.
So recently I got to know about UHPC, ultra high
Ultra
performance.
high performance concrete. Yes.
Yeah, concrete. So that, have you tried in these kind of applications?
Sir,
Because,
we have been using ultra high performance concrete in this kind of application since last almost 8 years now.
okay,
Earlier we used to import it from one of the company known as the product was Refotech. So
okay,
so we have used ultra high performance concrete, but you have to make sure that when you use ultra high performance concrete, don't use it in patches. Any kind of concrete which has a high strength, right? It may be concrete, it may be epoxy, anything.
okay,
You should envelop that. Otherwise, what will happen is whenever the structure is loaded, the stiffness, everything, as I mentioned, coefficient of thermal expansion, creep, modulus of elasticity, drying shrinkage is different than that of the original concrete.
Okay.
So if you do it in patches, it will debond. There will be a shear bond failure.
Okay.
Yeah. So if you jacket it, it's very good. It's a very good product, no doubt.
Okay.
Second problem with ultra high performance concrete is fire.
Okay.
So, because any concrete which is a high strength concrete,
Hmm.
because of the particle size compaction, right, which is used to achieve that strength,
Okay.
the water which is present in the concrete during fire tries to diffuse. There'll be pore pressure created on the cover and the cover cracks. So in that, to avoid that, what you can do is ultra high performance concrete, you can add some polypropylene fibers. So when you add
Okay.
polypropylene fibers, their melting point is about 100 degrees.
Okay.
So as soon as it melts, it will create tubes, like it will create pores. So it will allow the water to escape and pore pressure to release. So it will not crack your concrete. So when you're using ultra high performance concrete, and whenever the structure is susceptible to fire damage, make sure you use this kind of fibers as a hybrid system.
Okay.
Yeah,
I
thank you.
had another question is
Yes,
that
please.
you said the last stage where that they were you had divers, right?
Yeah, yeah.
So how much is below this the water level?
Normally, erosion happens depending upon the route or the tidal variation and other things. So we are doing almost about 6 meters below water, below the
Okay.
lowest water level,
Okay.
and the bed is about 15 meters.
Tile is about 15 meters.
Yeah,
Okay.
yeah,
Okay. Okay. Okay.
yeah. Thank you. Should I move
Very
ahead?
nice. Thank you.
Thank you, sir. Okay. So now another case I'm showing is a little offbeat case. So we do a lot of concrete structures, and as engineers, as Sarup Saab last time mentioned, that we don't think beyond. So this is a very good example of that. So we came across, a company where we're doing this. This is basically a refinery, and the question the client asks is, "यार concrete के structures तो आप करते हो? What about we have steel pipelines?" And the problem there is, because of the refinery, they can't do any kind of hot work. This is in the battery area. So how do we make sure that our infrastructure is safe? Because there are leaks in the pipeline, there is corrosion in the pipeline, and we can't do anything. They can't even do sandblasting or shot blasting to clean the pipes. They can't even do that. So over the period of 20 years of operation, these pipelines have leaked. So what they normally do is they fix, with rubber gaskets and clamps, they try to repair that leaks. But now the sectional thickness also has decreased. So there is a high potential or high risk of these pipelines getting fractured or damaged. And if so happens, there'll be a fire in the refinery. And if there's a fire, you can imagine the kind of loss in terms of asset and in terms of life. So they were worried about that. So we said, okay, we can create a pipeline around a pipe without even hot work. So that was the challenge we accepted. And the code we follow for this is ASME PCC 2015, which is known as repair of pressure equipments and piping. So we explored that. And these are some parameters like what is the thickness of line, overall size of the lining, what is the operating temperature, what is the overall insulated temperature, what is the design pressure, operating pressure, what is the material which is going to flow inside the, here it was blow down hydrocarbon, what is the external condition, because sometimes you feel that like you have lines which will be which will have a alkaline material flowing from inside, and external conditions are acidic, and sometimes external condition you have salt sprays and other things, so it varies. And again, the saddle supports, bends. So we did a pilot project for almost about 80 meters. And the target was that this pipeline, what we develop, should be a standalone thing. What do you mean by standalone is, if you remove the existing pipeline from inside, our pipeline should work. So we're creating a pipe around a pipe. And that should work for, so their service period expectancy was 20 years. They said, we want a service life of 20 years. So design as per that. So these are some calculations. I will not go deep into that right now. And this was the condition of the pipeline. You can see there were pockets, there were holes. Paint was paint used to peel off. They can't even clean the corrosion because that grinding also is not allowed in that zone. It's a totally hot, hot permit is not given in that zone. So what we did was, by normal brushing, whatever we could remove, we removed. And rest we applied. First, we applied a rust converter. I'm using the word converter, not remover. So what it does is it converts the soft rust into hard rust and forms a good layer. So initially we did that, and paint we could not remove because some paint was hard. It could not be removed by normal brushing, and we can't use any abrasive tools here. Later on, we all the saddle supports which were there had sharp edges. So we filled this cavity with micro concrete. You can see on the right, so that we can continue our fiber and connect that as well. Then we applied a putty to surface this. So we need a smooth level because there were some dentations on the corrosion indentation on the pipes. So there were a lot of pockets which were developed, multiple. So that had to be leveled first. So we applied a putty, and this putty is designed in such a way because pipe, unlike concrete, will have larger expansion and contraction in terms of thermal. So this putty should be able to take that. I mean, it should not crack. Then we went for first layer of glass, right? And then multiple layers of carbon. Now, why we did this was because carbon, when you directly apply on these steel pipes, and some of them are cathodically protected. So carbon is a conductive material, and glass is an insulating material. However, we are not getting that property of carbon in glass. But then you insulate your first layer. We had to undergo after this first layer, we had to undergo a holiday test. In a holiday test, what they do is they pass a spiral ring, and there is a current pass through that ring. So if there is any gap in between my fiber and my pipe, there'll be a spark. So we know exactly that there is some gap. It'll be treated. We'll have an indication. So it should be 100% holiday free, the first layer. And then you can go with multiple layer of carbon. Otherwise, what will happen is the carbon will conduct and in contact with steel, and there may be a chance of fire, or carbon can get damaged also. So this is the installation we did. And then later on, we applied multiple layers of carbon. So on the left, which you see is the first layer of glass. Then the holiday test was conducted. And then multiple layers of, carbon fiber were applied in orientation as per the design. Orientation and layers as per design. And finally, we have given a top coat of, UV protective layer. And this pipe we have guaranteed for an operational period of 20 years. And almost 7 years have passed. And there is no damage, no spotting, nothing of corrosion observed till now. It's 100% safe and intact. And after 7 years of operation, there is zero corrosion and zero maintenance. There is no maintenance now they're doing. Probably after 10 years, they'll have to go for just an overcoat of top UV layer. That's it. Only if it gets damaged. Then after that, we tried to explore what else can we do. So they had in their other plant, they had a problem in their heat exchanger tube. So they came to us that, now the problem is different. There is a heat exchanger tube, which is the section has reduced. So can you help us in that? So he said, let's explore that as well. Now, the problem in the heat exchanger tube is, unlike that pipeline, which had an operating temperature of 100 degrees, here we have 220 degrees. So we changed the resin and changed it in such a way that our resin would cure by heat. It would take about 260, 270 degrees. So similarly, we did this project, and they could save a lot, because otherwise if they would have changed the tube and the heat exchanger, it would have taken them a long period. We could complete this in 7 days, and with the cost of just 6% of that of replacement. Then we did, after doing this, so we further thought that we could do a little more. So we extended this to, in a fertilizer plant. These are IAT and FAT tanks, stores acids inside. And the problem here is they are lined and they get corroded very fast. So replacement cost of replacement would be 20 crores in each tank plus the downtime. Like it will take about 1.5 to 2 months to just replace this tank. So during that time, if the plant is shut, normally they have an annual shutdown of 15 days. So if you extend it to 1.5 month, per day they are losing 21 crores of revenue plus the cost of the tank. So almost they would end up losing maybe 400 crores. So in this, we could entirely do the project in about 7 crores. We could reinstate all the tanks. And we have given an operational guarantee of 5 years again on this. On the right hand side, what you see is the repaired tank. So in this, whatever we are doing is, this is not a standalone tank, like unlike the pipeline and the tube, but this is a compensating method. So whatever is damaged, we are only compensating that much thickness. And that's how we have given a guarantee of 5 years and not more. Right? So we are only catering to the only loss which has occurred due to the thickness loss. So yeah. So any questions in this or should we move forward? Yeah. Any questions?
You can proceed, sir.
Sir. So this is a very interesting case study we came across. It was a pharmaceutical plant, and we had an issue of the structure was structure was very safe in terms of design and other things, but some of the some of the infill walls, they were collapsing during earthquake, and this being a very prominent friend, so they thought that will not allow this, so let's retrofit this. So what was happening here was that some of the infill walls were failing during earthquake, so they wanted to stabilize that. Now in doing so, the earlier the structure was passing, but when we transferred that force to the wall, I mean when we were strengthening these walls, some of the members also would fail. So then how would we avoid doing that, right? So we used a technique of energy dissipation. I'll show you what we did there in that. Sorry, it's not playing. Just a second. So I'll show you an example of energy dissipation by this video. So AAC block wall of almost was subjected to 230 lbs of TNT blast. So that is almost to the same size that was used in Pulwama, or almost 1/3 that was used in Pulwama earthquake, Pulwama blast. And one wall was reinforced with wraps, and the other wall was unreinforced. And the carbon material which is used here also is very different. It's a different fabric. I'll explain you what's different in this fabric. So this is the unreinforced wall, and this is the reinforced wall. And this is a full scale exercise done in one of the universities in US. And it is anchored. This system is anchored on top and bottom. You can see the shock wave. Oh, sorry. Just a second. This is again gone. I'll just pull it. Sorry. You can see the shock wave and the heat wave traveling here and hitting the wall. Now you'll see the video from inside how it works. So here it is very important to see this. I'll just hold for a second here. The measured force outside was 184 psi, and that in the inside was just 1.5 psi. The approximate deflection, which was 4 inches in both ways in 10 feet of wall, which is AAC blocks. You cannot expect that, right? I'll show you the side view of this, which is very interesting. You can see from the side now. And this is a AAC block wall. It's behaving like a rubber band. Moved 4 inches on both sides and came back to its position. So how this system works, I'll tell you. And this is the photograph of this is the collapse wall and this is the reinforced wall. So now how this system, and in places where we had no problem in transferring the force directly to the wall, the members, we did helical bars. I'll show you that also. So these are the helical bars. They're just placed and anchored to the columns on the side. So the wall, right from the day we start and we end, it takes 16 hours to complete the entire wall with painting, with scaffolding and removal. So we had 230 walls to be treated. So some we did with this helical bar, and in other we used fiber. I'll show you that also. So this was fiber strap. Unlike that was completely wrapped because that was blast proofing, and here in earthquake we don't require that much. So we had just gone for small strips, as you see here. So these were the strips that we provided at every 400 mm center. Now how this system works, energy dissipation, I'll just go a little deeper into that. So basically in this, what we are doing is we are using two different modulus of material. So two different strengths. So one is in a normal term, we would call it a stronger material and a weaker material. How this works is whenever it is exposed to such kind of blast or earthquake, the weaker material will crack. It will allow the energy to dissipate. The balanced stronger material will take the rest of the, because the energy by then is diffused. You could see in that 184 psi to 1.5 psi. So almost 1% energy is left. So that then is taken care by the balanced material. And again, what happens is I'm increasing the ductility because area covered under the curve increases because of that, energy dissipation happening and the balanced material. So that is how we use this material, and all our design are based on energy dissipations. So in this, what we've done, the only disadvantage in this system is if in future there is an earthquake, a design level earthquake, the only problem we see here is that you'll have to redo this. But then the time and the cost is because if you strengthen the frame and do conventional method, it'll almost take us 6 months to complete the project with almost 25-30 crores. And this we could do it in 15 days during the shutdown. Of course, in parts, of course, in parts. And the overall cost would not be even 1/4 of the cost. And again, dust emission, because the maintenance practice which this company has is world class. You cannot compare that with any other companies in India or any abroad. So these are some photographs inside the plant. And you can see the level of hygiene they maintain inside is amazing. So without even, damaging anything, or this is absolutely a dustless procedure because everything is attached to a vacuum cleaner. So you don't actually spoil anything around, and you can actually retrofit the entire wall, and it's absolutely concealed. The treatment thickness is just 1 mm. So you'll not even realize that it is applied. And we complete the entire wall. In fiber wrapping, we take about 24 hours. And in helical bar, we take about 16 hours, right from the time we take that thing and give back. So that's the kind of speed we get here. Yeah, any questions in this?
Sir, you said it's a AAC block, right?
Yeah, AAC blocks. Yeah.
What size, sir?
So normal 600 by 200 blocks.
I see. Okay. But what I was expected that if it is a 600 by so and so sizes,
Yeah.
that much of impact when it comes, it should be break, you know. How it is expand like a balloon, I don't understand.
Sir, because see, inside it will definitely crush. But because there is fiber covering that,
Mm.
it will behave that way. Naturally, there will be some damage happening because that was a blast test, sir. Earthquake will not
Okay.
undergo that much. But there will be damage. See, damage has to happen.
Yes.
Only then will the energy dissipate. Like in a
Okay.
helmet, if your helmet does not crack, it will deform. And if it deforms, it will crack your head.
Yes.
Yeah. Energy dissipation should be there.
Okay.
Sir, do we have about 15 minutes? Chairman, sir, okay, do we have about 15 minutes more or should I end my presentation, sir? Hello? Hello?
Hello, hello.
Yeah.
Yes, sir. You can continue.
Thank you, sir. So I'll just do two case studies now more. One is about this weak phosphoric acid tank, and one about I'll take a heritage structure also. So I mean I'll be able to show you that also what we did. So with your permission, sir, I proceed. So this is a weak phosphoric acid tank, and mind you, weak acids are more dangerous than strong acids. Reason being they are more corrosive. So this was a phosphoric acid tank reactor, and the diameter was almost 37 meters and slab thickness 500 mm. So when they casted the concrete, because of the congestion of steel, the concrete did not go inside. And the tests which were recommended by the consultants were UPV and hammer, which itself is wrong. Because see, when you have a congestion of reinforcement, you should never ever go for any kind of these tests because UPV is ultra pulse velocity is a sound wave. And sound wave, how do you measure that is they take out velocity, and if the velocity is more than 4.5 kilometers per second, it is good concrete. So what happens here is if it's reinforced, a densely reinforced section, the UPV readings will be very high. I'll tell you the reason why. So sound wave, so velocity is measured in distance traveled in unit time, right? So whenever a sound wave passes through concrete medium, and if there are voids, it will take more time to come back. So velocity will drop. Now, in presence of steel, even if your concrete is not proper, because of the steel, the velocity will increase. And you will see that, you'll realize that you're getting good results. So in this also, when they did the UPV, they found the results were excellent, coming excellent. So they thought it was good. But when they started erecting the tank, during pegging, one of the peg went inside, and that is when they realized that there are voids in concrete. And they came to us, they said, we are getting good results, but how is it that these voids are there? So then we did tomography. Now, tomography is a multi-array thing, so it has 24 channels. It also works on the principle of sound, but it has 24 channels. So wherever there are voids, it'll show this red marks, and it'll show the readings will be. It's like a slice. You see a complete slice like image. So when we did tomography, we saw that there were huge voids, pockets, voids, piping happening inside. But when we told them, they said, "नहीं, इतना नहीं हो सकता है." So we said, okay, let's do one thing. We'll pour some water, we'll drill a hole, pour some water, and show you how it works, how much water goes in that. So and based on the area, we could find out that how much problem was there, which location the problem was there. So that is how we realized. And we started pouring water. We came to know. I'll just switch on the video, I'll show you. Just a second, please. and from bottom it leaked like this. You can see, sorry. So it leaked here, and there's a complete piping happening. So then we started opening up the patches, and we realized that there are huge voids. You can see. So because of dense reinforcement, the concrete was up ahead here. 50 mm cover, this became 130, 160, 200 mm above. The concrete did not go inside. You can see there are voids. So how we did what we started opening up. You can see all this was hollow. And imagine 10,000 tons weight was going to come on the material weight was going to come on here. So what we did was large voids were grouted by micro concrete. Small voids where honeycomb were there, they were grouted by microfine cement. And the top layer was replaced with concrete. And later on, we did completely tests again. So in that also, we found 5 locations which were again regrouted. So yeah, any questions in this, or should we move to the last one?
This concrete roughly when it was done, sir, this project?
So this was freshly done. I mean, immediately after concreting, they realized before
No,
construction.
the original structure, original project.
Yeah, original only, sir. This was about 7 years, 8 years back, sir.
So that time this self compacting concrete is available.
Sir, it was there. So that is the exact problem. See, the consultant did not recommend that. Secondly, the consultant suggested a wrong test which was to be conducted. UPV and hammer cannot be constructed in densely reinforced concrete. So this was a disaster, sir.
All right, proceed.
Yeah.
This test you are doing is a UV test.
No, it's not UPV. It's a tomography test, sir. It's a so UPV is ultra pulse velocity.
Yeah.
And tomography is a much more advanced version of that, sir.
Okay. What do you do in that?
Sorry?
If you can kindly educate me. Tomography.
Yeah, so tomography is a multi-array system. So see, in UPV, you have one transductor and one receiver, right?
Right.
In tomography, you have 24 channels.
I see.
So one channel sends signals to another 23, and similarly, another 23 sends to another 23. So you're creating, it's like a X-ray and a CT scan.
Okay.
You can see through the concrete. I mean, where the voids are, how much is the proportion of voids.
Okay.
Everything can be seen, sir. Here you can see. So yeah, any more questions, or we move to the last one?
Yeah, please move.
Yeah. So this is City Palace in Udaipur, and I was lucky to be working on this project, especially with the Shriji Arvind Singh Ji Mewad, who was the Maharana there, previous one. He just passed away a couple of a year back. He passed away, and he is one of the most brilliant men I've ever met. I mean, very visionary, very well learned, well read. So City Palace, as you know, is built over the hill and built in phases. So these are the major, and every Maharana who was there built their own structures, added. So it was right from Maharana Uday Singh to present Maharana, who is Lakshmiraj, Mewad. Everyone has done their own construction. So, and these are the 8 major phases in Udaipur. So you can see the construction. So, and you can see trees on the top also. So it's built over the hill, built in phases. So what happened was, when it was designed for a ground floor, and suddenly you see 6-7 floors are added on the top. So the ground floor started cracking. So once it started cracking, the common thing was they added walls to avoid that load to make that load transfer happen. And large walls, I mean walls starting from 600 mm to 2-meter thick walls were added. And our aim was to remove all these walls and create a hall, create a space which was there earlier. At the same time, make sure that the structure is safe because there are almost 15 to 20,000 visitors per day. So our intention, and one more thing was, there was only one entry and one exit to the Salekhana, which is a very prominently viewed structure. So our aim was to create another entry also to the oldest wall of palace. We had to cut through that wall. So initially we did some survey also of the land, GPR survey. So we know what is exactly below that, what area is in cutting, what area is in filling. I think there is a background noise. And after that, we did some crack monitoring also on the walls. But we realized that those were all majorly because of the thermal expansion. Hello.
Can you identify whose mic phone is on?
I think Satish sir is there. I think his phone is on. Yeah. So this is how we started opening the structure, supported the structure because the live load was still on, and started partially removing the walls by supporting and then strengthening this existing thing by helical bar system so that we can regain the load path. We added some pillars also in some portion and anchored it to the existing pillar so that it becomes monolithic and load transfer happens to both. Some places steel structures also were created, and these were infused by ultra high performance concrete. So in case there is a fire or something, we have at least 2 hours to withstand that. Now this was very interesting room. So on the right you see is the oldest wall of the palace, which we had to cut through, almost 2 meter thick. So we used soak fix anchor here. So if you use normal anchors, what will happen is whenever there is earthquake or any movement, these anchors will transmit load to the random rubble masonry and it will crack and it will disengage. Soak fix anchor I like by a shock absorber of the bike. So it is an outer layer which is flexible, which goes inside the concrete, and the reinforcement which is at the center. So if there's any moment, stress transfer is not happening, load transfer is happening. And left hand side you see this is a very interesting room. So there are 4 rooms nearby. Left hand side what you see is the oldest wall, almost 1550. This is 1600 or 1700 century. This is about 100-year-old, and this is about 50-60-year-old. So 4 different centuries and four corners. I mean 4 different parts. Very interesting. So we built because we had to cut diagonally through, and again the room nearby was 7 feet higher than the room just adjacent because it's on a hill. So we had to diagonally cut through. So we created a retaining wall inside, then started cutting this wall by wire saw, and then started removing. After fixing those anchors and plates, we started removing the masonry from inside and started fitting girders inside. And this on the right hand side you see this is the cut portion by wire saw, how smooth it has cut. And this is a 500-year-old structure wall, random rubble masonry in lime mortar, yet you see nothing has come down. And here you see the room which is at higher level, and this is almost 7 feet down. Now what we realized was one problem was that after we went about 7-8 feet down, we realized there is no foundation for this wall. So how will the load transfer happen? So then we prepared a transfer girder here, created foundation on both sides, and transferred the load of this specific wall to that girders through this girders. And this is the structure completely after removal of walls. You can see it took us 4 years to do this. I mean 2 years in design and 2 years in execution. Yeah, this is the actual photograph of the gallery after that. Yeah, any questions in this? Yeah, so thank you so much everyone for listening patiently, and thank you, sir, for giving me this chance, sir.
Faizad, it
Sir,
was a splendid
sir, kindly say,
presentation.
sir,
Just a
kindly,
minute. Just a
sir,
minute.
Yes, sir.
Just a minute. Can you please hold on? Kaizad, it was an excellent presentation and a very, very meaningful presentation. I'm so proud of you
Thank
to
you, sir.
have done these kind of things.
Yes.
Now, I'll tell you the reason why I just brought this as the second presentation. It's a very, very important reason that for all of us to learn. We are finding that the old pipelines that have been laid down the ground, especially for utilities, they are almost like giving up everywhere. We had this problem in the city of Indore, which had been claiming as one of the finest maintained and clean city. And unfortunately, we had the problem where the sewerage lines they got mixed up with the drinking water because there was hardly any maintenance or repair or rehabilitation. And the net result was that we ended up plenty of casualties and plenty of sicknesses. Now, the sad story is that this is the thing which is repeated town after town, and basically things are happening here. This was one of the reasons why I thought that we should be deliberating on these issues. Second, which is again very important, our bridges, our flyovers, they are also passing through a very, very terrible phase. Many of them had been constructed almost like quarter of a century ago, and now they are giving up. Ironically, the older structures that were constructed during the British regime and thereafter, they still exist, robust and serving. So there is some problem. We don't have any tools of investigation. Ironically, these tools are available and they are being applied right here in India. And that is what makes me so proud that you have been able to bring out these things. I have three appeals to all our friends here. Number one, I am very sure that you have learned a few things here and you have understood that where exactly to go and find out the solutions from. And the answer is simple. We have to sit down together like we sit in the family, sort out the problem. We have multiple talents. And I would very strongly advise that in your neighborhood or in your realm, if you find that such kind of things are existing, please feel free to advise them to come in and seek advices. There are proven cases available with us, remedies that are available with us, and it will be a shame if we do not transfer this. So, as members of ECI National Register, I would expect all of you to start talking about it. Disseminate the information. That is something that I want. And also try to bring in many more engineers who feel proud to be called themselves as engineers to come. We have to learn from each other. There are multiple experiences that have, I'm very sure that many of you also have stories to tell. And it is the stories that we are lacking these days. So please come forward, volunteer, send your names, and every weekend we'll have this particular series. In the coming week, there is another very important issue that I would be taking up. Of course, I'll tell Yogaraj to send it to everybody that executing the work is perfectly fine, but then there are aftermaths, and the aftermaths relate to the commercial issues. There are contractual disputes, there are aberrations, there are changes which have very adversely affected the finances of our corporate houses. And I'm not referring to the large corporate houses, I'm talking about the good, honest service providing houses like most of us are. So, we'll be talking about how to resolve the disputes and things like that. And that is another thing that will be coming up in the calendar. Thank you very much. And if you have any point, Kaizad is here and please raise it to him. If you cannot raise it now, please think about it and send the questions to Kaizad, and he'll be very happy to answer. Thank you.
Uh, Thank you, Chairman, sir, for the opportunity. Thank you. And thanks, my fellow engineers, to patiently listen to me. Thank you so much, sir.
Thank you, sir. But sir, kindly share your contact number, sir.
Sure. Should I share in the chat box?
Yes, yes, please do that. Let everybody know who are the people who are delivering to our country. And then tomorrow, they are all going to go together. We are all going to go together to make sure that wherever the rehabilitation, repair, anywhere in the world has to be done, it should be done by us. Let us make ourselves proud to be the biggest makers of the infrastructure. Thank you.
I've already shared my contact in the chat box, sir.
Thank you, Kaizal. God
Thank you
bless
so
you.
much, sir. Thank you.
God
Thank you.
bless you.
Thank
You
you so
have been
much.
wonderful. Thank you
Thank you,
so
sir.
much.
Thank
Bye,
you, sir.
bye, bye, bye.
Bye.